Hello, uh, we considered algorithm, Kruskal algorithm, and its implementation that works for O n squared. In this implementation, we check uh, that if every time, each time if vertex included in some component, uh, we just uh, it works for On, and that's why we have O n squared implementation in this case. So I suggest implementation based on disjoint set first. Uh, we consider uh, connected components in Kruskal, and we just want to in every component we have trees. This graph is just forced then, and we want to connect each component, and we want to connect each component and do only one component that contains our MST. So we want to check if there's a cycle. It means two vertices are included in our in in one component. Otherwise, we just union sets and say that this will be a new component. So this operation, all of these operations can be performed for all again, and we're gonna use disjoint sets. So we need union that unite that merge two sets. Two distinct sets. And another operation calls find set. This operation just return element is called representative. For every component, for every set, we we store some representative element, one representative element, and we want to find it just using this operation, and make set is just operations that works for all one. So we are going to use disjoint set first implementation. and for each set, for each set in disjoint set first, we will store as root tree. What I mean by root tree? If you consider two sets, for example, C, H, E, and FD. Root trees for these sets will be C, H, E, and FD. Trees can be different, and this is one representation of how we contain it, how we can represent it. Okay, and FC elements are representative for these sets. And for each element also we are going to store parent and size. So we store where is stored PV parent and what and size. Size of elements in subtree. If v is represented, no, if a is root, just or if okay, and forget about we consider some we consider our task, our Kruskal algorithm. In this task we have some graph. Forget about this graph, we consider a new task, and edge of this tree are unrelated with edges in the graph. So how can we check, how can we find representative element for element in each set? We just check if px equals to -1, it means it's representative. We just return this element, and otherwise we go to the parent. Your climb to the parent. And second operation, union. Union over, we take two elements for that contains that contain in different or is contained in different set, and we want to where is it? And we want to union components. How can we do it? We just for these elements we find representative elements, find set, and then we just check that U not equals to V. They are in two different elements. They are in two different sets, and we are union them. We consider trees of these elements. That means sets, and if size of some set, size is that count of elements, is less than size of other tree, we just create edge between representative element of sets that have less vertices and other representative element. So if size, we call it UMV, if size U less than size V, we swap it. We swap and we just подвешиваем one tree to other tree, and increase the size. Now we can find answer. Find answer on every query for in all again. Why is it true? Notice that if we consider trees, two trees, and want to union them. For example, in this tree there are y size, and for second tree their x size, and if we union them, we can when we get that in in um, in bigger tree, we get at most 2x size. And step, it means step to the parent increases size at least twice. Step to parent increases size at least twice. And depth. Therefore, depth depth of all trees less than all again, less than all just all again. That's why we can get that's why this operations performs for all again, because we have depth less or equal than all again. That's all about disjoint sets, and we can apply this data structure in our algorithm and get that this algorithm that works for that based on this data structure works for all again. When log n or m log n, сейчас n log m log n. Where m is count of edges in our graph. And let's solve some task on the code. Second, we are going to solve task based on Kruskal algorithm. 1 minute. Do you have questions about this algorithm? Ah,
No.
no. Okay. No. This is obvious, I think. Look at symptoms complexity. Okay. I'll find some task. Ask about master. Unfortunately, I didn't solve this and this task before seminar. And this task is more interesting in theory than this. We need to find critical and pseudo-critical edges. What is pseudo-critical and critical edges? If you have some graph, critical edges of MST will be critical edges of this graph will be edges that included in every MST. Here for 4 different MSTs, and this edge and this edge will is are critical edges, and pseudo-critical edges are edges that included in some MST. In every MST we don't have this edge, for example, and this edge will don't not critical, doesn't not critical.
Получается 0, да, например, будет в
Ну,
этом случае?
так, где 0?
Ну, я имею в виду, будет... как вы еще раз назвали ее, вот когда они где-то есть, где-то нет?
Ну, вот у нас есть, ну,
А,
критические,
псевдокритикал. Угу.
псевдокритические ребра, они, они не содержатся ни в одном МСТ.
0,1
0,1,
получается,
0,1 же
или нет?
содержится. 0,1 это, наоборот, критическое. Оно
А,
содержится во всех.
ага.
Вот, и 1,1, и 1,2 тоже критическое, оно тоже во всех содержится.
Угу.
А вот, ну, например, 1,4 не будет вообще ни,
Угу.
ни псевдокритическим, ни критическим. Оно ни в каком графе не содержится.
Угу.
Вот, только, ну, у нас вот только 4 возможных МСТ есть.
Угу.
Вот, и, ну, псевдокритические ребра, они не содержатся ни в одном из них. Вот. Ну вот, тут напечатан ответ.
Угу.
0,1 у нас критические ребра. Ну, это в смысле по нумерации, если смотреть. Ну,
Угу.
левое ребро, первое ребро, второе ребро и так далее. Вот 0,1 у нас критическое ребро. Но в
Угу.
ответе есть. Ой, да, 0,1 и 1,2. 1,2. Первое
Угу.
ребро, оно есть в ответе. Вот, и 2, 3, 4, 5 это будут критические ребра. То есть 2, 3, 0, ну да. Так, 2, 3, 4, 5. Ну, все, кроме 1, 4, короче.
Угу.
Понятно, да?
Да, спасибо.
In this case, we have... прости, я буду говорить на английском, потому что еще смотрят люди, наверное, на ютубе.
Угу.
Так, ну, in this case we haven't critical edges because we can delete any of it and get MST. So we don't have critical edge, and all the edge will be pseudo-critical. So, what constraints? Constraints is very small, by the way. 100, 100. What does this mean? What is the constraint? Time constraint. Where is the time constraint? Okay. We can solve it by O(n) squared, even O(n) squared log m. 100 multiplied by 100 multiplied by 10. Okay, and when we it means we can apply these algorithms Prim and Kruskal many times, each time on some edge, I think. Okay, and if we consider every edge, we have this graph, and find for this graph, if we find for this graph MST, we get some weight of this graph. Weight is count of is total sum of weights of edges. Okay, and then we if we doesn't in if we exclude every edge and launch Kruskal algorithm, if we exclude critical edge, we get bigger weight. Okay. And if we disclude non-critical edge, pseudo-critical edge, we get the same weight. But how to отличить pseudo-critical edge or just usual edge? We can отличать.
How to distinguish.
How to distinguish some pseudo-critical edge from usual edge. Do you have an idea how? We can exclude and include some edges and get different weight of MST, of our MST. Блин, I don't know. Сейчас. How to distinguish pseudo-critical edge from usual edge. No, for example, consider this edge. If we exclude it, then we get. Okay. I got an idea. Так, ну. Trying to exclude edge by edge, I think. We can try to exclude edge by edge and find MSTs and get if we it's obvious that I didn't start recording. Сейчас. 1 second. I mean, okay, if we disclude edge by edge in this graph and find MSTs, we get, if we delete this edge and then this edge, we get that our MST decreases. don't know. If we exclude this edge, then this edge, then this edge, how to distinguish this edge from this edge, from this and this edge. So in MSTs, if we find MST of this graph and exclude edge by edge graphs and get graphs and find in this graph MST, we get that when we exclude some edge, we get and included, we get that this edge no okay, we include in some MST this edge, and then we find MST of graph and show that this graph if critical edge is embedded in MSTs, in intersection of MSTs and pseudo-critical edge. Embedded in G without MSTI. And get that and we get that if we find some graph and include in our MST some edge for example, if it's pseudo-critical edge, and we include it and find MST doesn't change. And if we find if we include pseudo-critical, include usual edge. By usual I mean non-pseudo-critical and non-critical. MST increases. Do you get my idea?
Yes.
Yes? Okay. Okay, we can implement and using Kruskal using Kruskal algorithm, and Kruskal algorithm will based on disjoint sets. So we want to use class disjoint sets. Disjoint set. In this class we want to implement find set that returned in that will return if what is it here we implement find set and union if p that we didn't define return x. If other case we return find set from x. In other case we just implement union we find for them representative elements and if they're equal we just return. And every set will contain in we for this implementation, for class implementation, we use just vector of ints of parents. And if size u less than size v, we swap it. Swap them. Other case we just declare parent and increases our size. For constructor we так. Go find we construct our disjoint set. How? We just we don't want to do it. Сейчас, 1 second. Что нам понадобится? Let implement it and look what we can. What we're gonna use. Okay, we sort all the edges. We can sort it by index and then by weight. Or we just can sort it by only or only weight. Let's think. In our implementation, in our pseudocode, we use Prim. We didn't use indexes at all. We just use edges. So, but in this case, we are gonna we are going to disclude and include edge by edge. That's why we can sort edges. I don't remember comparator. We don't. Comparator is needed or not? For vectors, I think not. Or сейчас. Ладно, потом узнаем. Okay, and then we just de-exclude and include edge by edge and apply Kruskal algorithm. Okay, and let we Kruskal will just call it from our edges, and Kruskal will return weight. Total weight of graph of MS10. I think about variable name. No, let it be MS10 total. And we just edge by edge we disclude and include it by in Kruskal. Okay, in second in second argument of Kruskal, we just put edge that we want to include. Just index, I think. Так, include. And in disclude. Equals to -1 if we don't want include or disclude edge. So for edge auto edge and edge, we just include edge or disclude edge. Include edge or disclude edge, and where we contain result in vector of vector. Okay, we have MST total. We just disclude edge if edge we want to contain indexes, by the way, of edge. We put them to a result. We just include it. Так, if Kruskal of edges let disclude then include, I think, or disclude then include to эконом. Сейчас подумаю. Second. Ну окей, just include or disclude. Okay, include edge of v, just e. Okay, and disclude nothing. And if we include on edge, and if MST is increasing, MST total is increases, сейчас, we just call it as pseudocritical, and push this edge to result. Result 1. Push, because we want to push in pseudocritical. And by the way, Okay, and return if continue, I mean. And if what? If we disclude our edge from st and it decreases, then we push it to other array and continue. Oh, continue. Okay, don't write continue. Just else if okay. That's the algorithm. And we just return mst total MOE result. Okay. Now implement Kruskal algorithm. We have edges. We have some set. We have weight. We want to calculate total weight. We don't use null. We don't use where is Kruskal algorithm? We don't use the set because we don't want to contain edges. We only want to calculate our weight. So we just use our disjoint set. Disjoint set, how? Disjoint просто. Disjoint set. Disjoint set mst. Okay. And then we just iterate through all the vertices and make sets. Let me think about it a little bit. How can we do it faster in this case, in this task? We can create constructor and put in this constructor vertices just int n, int n and make sets. How can we make sets? We just call parent. Нет, we just call initializer of our constructor of array, and size will be include or disclude. Okay, disclude vertex size and null. It doesn't matter, include or disclude. That's all. That's also constructor. Okay, we just create disjoint set with okay, сейчас our disjoint set with count of vertices. So we want to include it. And then n. That's all. Okay. Нет, Kruskal. Always you can check like this that you do it correctly. Okay, and you call from n this constructor. This will be our disjoint set, not mst or mst in this mst and Kruskal. Okay, we consider Kruskal grid and this will be mst. Okay, and we want to do mst. How can we do it? We just iterate through all the we already or don't. Сейчас, 1 second. We can sort it by weight. We have to sort it by weight, I think. But we have to sort it by indexes too, because we consider this order. Okay, that's why we can use edges that sorted by indexes and edges that sorted by weight, I think. Okay. We call let me write it, and then I sort just order by weight. Okay, then we just call find set of winware. I think I do mistake. This так, where's can iterate through edges. Okay, we iterate through edges and call this. We iterate through edges in this order. Так, чуть пишу. To edge, and we just check find set mst find set of edge now edge edge now and edge 1 and h1 not equal to mst find set h1. We want to union it. No, we already implemented this and this. Okay, we just union. We're just trying to union them. mst union winv mst union h null and h1 h1 and h2. In first argument we contain weight. So that's all, I think, and we just calculate mst. How can we do it? How can we do it? Calculate mst. Calculate size. We have some set here, but we can так. Second. No, we can call this just call this and call this, and then we just total weight h null that contains weight. That's all. Return total weight. That's the idea. Так. We can put third argument in this. Just 1 second, I think about how can we provide edge order by weight. Okay, we can we can just call it from order by weight. And in this case we want to create structure, another vector, in this case we don't want to sort. I think about, we don't want, we так, 1 second. Oi, it's it's harder than I think, and because we include we include and exclude in our, then I think about how can we do it. How can we do it? We can create another function that included or excluded or in our graph edge, and sort it again and again. So I mean by binary search included in the structure or just excluded. That's too hard algorithm, I think. Do you get what's the difficult? Each time we sort our graph, we want to avoid it. Then we just sort it one time, and we want to include or exclude edges from our graph. In this case, we can sort it only one time, and by binary search we include edges in our graph to support order, or just exclude. Okay, but can be solved easier. Do you have ideas? Solve them.
Not so.
Not so. Мы хотим просто поддерживать порядок и вызвать сорт один раз. Вот здесь вот вызвать сорт один раз. И потом просто включать и исключать ребра в зависимости, ну, поочередно, да, и мы хотим поддерживать порядок. Чтобы включать ребра, нам просто нужно okay, we don't want to do it, by the way. We included in this we included before we we included in MST before we after we sorted. Okay, I think I got the idea how to do it. We disclude it. We can disclude it in this vector, but we can include it only in set in MST. But there's mistakes. There we can get mistake. But the idea is correct, I think. We just include it in MST and exclude it from our edges. Okay. We include some edge. If include -1, then we just union in this case we edge order сейчас we need edge order by indexes. So we check we just include null and 1. We include this edge, necessarily include this edge, and then we just do this, or we just exclude, but from our graph exclude from what? Так. Окей. Ага. Так. Это не очень подходит, потому что окей, застрял немножко здесь, но тебе идея понятна?
Да, в принципе, да.
Понятно. Ну, весь код понятен, в принципе?
Ну, да.
Ага, хорошо. Ну, то есть я хотел исключать, когда мы встречаем, точнее, исключать из вектора, из самого массива с весами, и включать саму st. Но тут дело в том, что у нас индексы здесь и индексы здесь, они, ну, они различные. Да, мы хотим получать, по сути, индекс в вот этом массиве по индексу в вот этом массиве. То
Мгм.
есть нам нужна какая-то мапа, которая приводит индексы. Вот что-то как-то это сложно слишком. Короче, наверное, ну тут полегче надо что-то придумать. Я публикую. Ну, ты уже все понял, наверное.
Ну да, в
Там
принципе.
чуть-чуть по-другому код будет написан, чуть-чуть по-другому, но я его потом
Мгм.
опубликую, хорошо?
Да.
Вот, ну, не знаю, надо тебе ли это. Ну ладно, все. We need we need contain in if we want to do it like this, we need to contain map that from that take index from that take index and get from hash order by indexes and get index in this array. So I can we can do it. I think we can do it easier, and I will send solution, and it will be different, but use these ideas. That's all, I think. Спасибо. Ну, пока. Давай.
Я хотел спросить,
Ага.
вы видели, я скинул там